1080p, but 1080i.
1080i. Yes. I have no idea why. Let's see how that goes. All right. Guess we might as well start. Sorry, I'm just gonna go around. Sorry, what was your name? I can't remember.
Dark.
Dark.
Yes.
Have you've been here before?
Yeah, I came last month. That was
Okay.
the first time. I've been
Gotcha. Cool. You're Mark, if I remember correctly.
Harold, first time.
Harold, first time. Okay. And
Greg,
Greg. Right.
and I've got, if you've got time at the end, I've
Yeah.
got a presentation on the zipper and Coke.
Oh, right. Yeah,
Oh, cool.
you mentioned that. Cool.
Yeah, so I made that presentation in 2008, so I may not remember very much about what was going on in it, but it was a kind of interesting project.
No, I'm glad. Hopefully you can.
There'll be a
pick up
formal
my
verification of zipper in Coke with automated translation to Haskell.
Nice.
The interesting thing
Yeah.
for me is Greg, I think, is the first person who I ever heard talk about Haskell back
Okay.
probably 5 or 6 years ago. I don't remember how long ago it's been that we met, but it was,
Sorry about that.
it was a long time ago.
Cool.
So,
I'm trying to think if I have any interesting news I came across recently. Can't say I have. I've been super busy, so I haven't had a chance to scour the web and find cool new things about Haskell or just functional programming stuff in general. I did hear that .NET Core got released recently, and apparently F# is working on it. After like 2 weeks, they released it, but I haven't tried it yet. So if someone gets a chance to go do that, let us know how that works. That'd be great. We're all about kind of using F# in this group a little bit more than the Windows folks are, or people who do .NET for a living every day. All right, so I want to talk about the zipper data structure. There's a paper that I came across recently, and you guys named Gerard, maybe? I'm not sure. I can't remember. Hewitt, something. Hewitt. Yeah, Gerard Hewitt. Apparently it's part of the functional Perl maybe book. I'm not sure exactly.
I
But
think that was a series in a magazine that they did.
okay. Yeah. So. Yeah, it's yeah. I took a look at it. I was like, I don't know what this is. I've seen a lot of people throw this stuff around, and I'm not sure what it is. Why would I use it? What problem does it solve? I have no idea. So I read the paper. It's like 6-7 pages long. It's not very much. It's like one of the shortest papers with code example I've seen. And it's not double-sided. It's just a single flow. Right? So that makes it a lot easier. And I don't want to just talk about it right out from the front as to what problem does it solve. I kind of want to take a little crappy little story and talk about, hey, we're going to start here. We're going to go here. And hey, how do we do whatever we want to do? So, in a nutshell, the zippers are a data structure that sort of combine. They're sort of for doing traversals, if you will, in a optimized fashion across any data structure, and typically any recursively defined data structure. I don't know if that makes a difference. I don't know yet enough about it to say whether it's for all data structures or for just recursively defined data structures, but I can see it being applied to pretty much anything. But that's just from my point of view, limited point of view so far. So I thought, the paper, the reference a tree. So I don't really want to build my own binary tree. Plus, honestly, Haskell's not that difficult anyway. But I was like, you know what? I'm just going to use the containers package as this data tree package. And the data type is pretty simple. It's a tree that's polymorphic, some over some type, and either has a node or a label, if you will, and has a forest of other trees. And the forest of trees is just a list of other trees. So it's a tree that has a value and a list of other trees next to it. Nothing particularly complicated. I was like, okay, let's start with that. So, here's my little tree. Doesn't make much sense. I actually copied this from the Learnio Haskell for Great Good. So if you read that chapter on zippers, you know where I'm going with this. But I modified, instead of their tree, I was using this generic tree, basically, not a binary tree. So I've got this tree. I defined it for a string type. It's not polymorphic. I just over the string type. Let's see what I'm REPLs here. Make that a lot bigger. All right. So I've got this function, draw, and I'm going to print out my little tree. Right? If you read it, left to right, top to bottom, it's like Polly wants a chip. I could put cracker in there because it didn't fit. So I just changed it to a chip. Right? And so we've got this tree, which is cool. So what we want to do now is, like, okay, we'd like to modify some value in this tree. Right? It's like, well, crap. Right? Modifying a tree in any language is not particularly the simplest thing to do, especially if you know where you want to modify it, you need to figure out how to get there first, and then modify that one particular bit, right? Doing it in an imperative language, it's much easier than in a functional language, simply because if you know where you're going, you go there, and you just change the value to whatever you want, and you leave. Right? There's nothing else for you to do. But in functional languages, like OCaml, Haskell, F#, stuff like that, let's exclude F# from OCaml, actually. Let's just talk about Haskell. Because they have mutable stuff in there. It's not really what we want to talk about. If you modify any value in Haskell, you're modifying literally just the value. If you modify, let's just say you've got a 1, and you multiply a 2, or a 3, you're not modifying those integers precisely, you're creating a new integer. That's just how it is for all data types in Haskell. Like you said, well, let's do it. So you're just modifying any particular, you're not modifying the contents of the data structure, you're just modifying, you're getting sort of a new one out of there. That's what you're doing. So if we've got this, Polly wants a chip over there, tree there, and let's say we want to modify a W, right? Or replace it with something. Doesn't really matter what it is. Right? Sort of the first and sort of simplest way to do it in Haskell, and also the most tiresome way to do it, is using pattern matching. Because that's just, Haskell lends itself, it kind of gives you that sort of stuff there. And I'm going to go all the way down here so you can't see that. I'll talk about how you can change that little W that's there, right? So we'll change that W on the right-hand side, you'll see what triple X is. So what we do is we're saying, okay, let me see if I can pull that. So we can get all of this on the screen. So the way we kind of do pattern matching in Haskell, you can do this on any data structure. Pretty much rip it apart, explode it, and you change the piece that you want, and you put it together, right? And Haskell behind the scenes doesn't create an entirely new data structure for all the components. It only replaces the one that you have, and so it uses stuff like structural shared something or another, so that your data structure, your data doesn't get duplicated, basically. And so that W that ends up over there is simply replaced with triple X, because I was like, I'm lazy. So that's sort of how you can pattern match on any data structure, and especially this particular tree data structure, and say, hey, I want to replace that W with a bunch of X's. And for anything that doesn't match, just return whatever that was originally. So if we go to our little shell, and we could do change pattern match, and let's just provide it just a garbage node, simply because let's try and see what this says, right? And you'll see that it's still foo, and it's got nothing inside of it, right? So it works for stuff that doesn't match what we want it to. Well, drawing it's boring, because apparently it's only one node. Drawing foo bars is foo bar, right? Nothing fancy. It works on stuff that we don't care about. Now, does it work on our little poly guy? And we can see, yes, it changed that W to a triple X, right? Which is great. Hooray, we did one thing. Now the problem becomes, okay, what if I said, I want to go modify this thing over here, right? This H. Now, if we go back to our code, I really hate writing that. I don't want to write that. That's a terrible way to change stuff in a tree, right? Because imagine if we had a generic tree that a user provided or someone provided to you, and like, oh, I want to change that one. So what, you go write a new pattern matching function for each single time you want to change an element in the tree? That's really annoying, right? So remember talking about sort of traversal and directions and things like that. So one of the things you can do is say, hey, listen, I know how to sort of go from the top node to the children to some node in there and its children. So basically, I know ways sort of how to traverse into this tree, right? What if we could get a list of directions, right, and then go inside that tree? And so all the user will have to do is provide either a left node or a right node, and then we could traverse. So for instance, let's say we're up here, and we have this cool new function, change with direction or something, and we say, hey, I'm going to give you a right, and then a left, and then a right. Okay? So right, left, right. So if I provide you 3 directions, you should be able to change whatever is at that location. Right? That's a little bit more sane in my mind than writing a new function for every possible combination of change. Right? So what does that sort of look like? Right? So we'll create a little data structure or data type, left or right value. Those are the only 2 values it can possibly have. We'll say, okay, we're going to define this thing called change directions. It accepts a list of directions and then a tree, and it outputs another tree, or outputs whatever ends up being there, a tree. And you'll see over here, I've defined my function in terms of pattern matching. Again, one of the nice things I like about Haskell is like when you want to be declarative in terms of defining your functions, you can. And I just really like having that. So what I'm saying is over here, let's just take a look at this first example. I'm saying, okay, if I get a left, that's the beginning of the list, and the D's stand for the rest of the directions. And then if I get a node with some value, and then it's got a left value, and it's got a right value, then return the node with the value that was there, but then recursively call change directions with the next set of directions with the left tree, subtree if you will, and then cons that with the right side of the tree. So this change directions DSL will end up running. The result of that will then be cons onto the R. Am I using that word right? Cons? Yeah, I think it's like supposed to be appended. So let's just use append. So basically it says, if I get this left direction, I'm going to try and go as far as I can to the left, and then add that to the rest of the tree over there. But if I receive a left, I don't care what directions are, and if there's no trees, no children basically, I'm just going to return the current node. Because it can't go anywhere further, right? So it just kind of returns the same exact node that there is. On the right side, it's like, okay, we sort of do the same thing, but since remember we've got this list of trees, left I'm saying that is the leftmost of the list, but right is anything to the right of the leftmost of the list. Because it's not a binary tree anymore, it's just here and a bunch of stuff over there. So what I'm saying is if there are at least 2 elements of that the subtree, then go down the right side of the subtree as far as you can. Right? And over here, sort of the same thing. If you give me a bunch of list of directions and there's only one element or there's no elements, this L will match either 1 or nothing. And so it's just return the current node because there's nowhere to go. We've already been left. We can't go anywhere. And so down here, finally, when we get here, we're saying, okay, if there are no more directions that are left, because that's our case when we actually want to change something, when there aren't any directions left, and we don't really care what the value is because we're going to substitute that value, and how many ever children there are there, it doesn't really matter. We're going to replace the value with a bunch of x's. Right, so does that sort of make sense?
Is there a specific reason why you didn't just make it a binary tree, or is it just simpler not to?
I just decided not to.
Okay.
Just kind of give you an idea of, like, it doesn't have to necessarily only work for binary tree. Your tree over here could be represented as a binary tree or just arbitrary type of tree. So does that kind of make sense? Like that thought process of saying, I don't care how big the tree is, give me a list of directions, I'm going to try and go in that direction. As much left as I can, as much right as I can, just give me the directions. And I'll change whatever it is when my list of directions are empty. All right, so let's see, change directions, remember we said right, left, and then right. And we'll change totally, and we'll draw it. So, let me see, we went right, we went left, and we went right. We just end up changing that down there. So now I don't have to write a bunch of functions, I can just do whatever the heck I want. If I put a bunch of arbitrary stuff in there that doesn't exist, then it won't do anything. Which may not be what you want, but it's good enough for an example. We just go right, we change the top of the tree, right? Do the left first, right first, we'll change that Y to a bunch of X.
If it's empty, does it change the top node?
Well, let's see, I haven't tried that. Yep. So hooray, that's one step better than the last step. But the sucky part about this thing, like as cool as it is, and when I got this working, I was like, wow, that's neat. Hooray, I did it. As neat as that is, you know, if you're editing a tree and you're constantly editing it a lot, right? Especially if you have a bigger tree. One of the problems with the change direction thing is you always have to start at the top. Always. You always have to start at the top and then traverse to wherever you're going. And if you want to say modify this guy and then say that guy consecutively, you always still have to start at the top. There's no way for you to go from here to there. So it's kind of sucky that way, right? So when you think about it, the Learning Haskell for Great Good, the zipper chapter specifically is probably good. The rest of the book is good syntax introduction. But that zipper chapter is actually really nice and explaining that, hey, you know, once you've kind of got this traversal thing down, and I think this is sort of quite a bit of the paper as well. It gets this far. It gets a bit further as well, but I feel like it doesn't fully explain to you how to get there, I think, what the entire concept of the zipper is. But anyway, so the Learning Haskell for a Good book, they basically say, listen, since we're already kind of traversing, right, we know we're going right, we know we're going right, we know we're going right, why can't we just keep a list or some semblance of, hey, let's leave some breadcrumbs, basically. We know we're going right, so why don't we just store the fact that we're going right? Why don't we just store the fact that we're going left from here and then right from there, right? And at the same time, you know, as we're traversing, we know where we've been previously, right? We know we've been up here. Like if we're down here, we know we've been up here. And if we're over here, we know we've been here. And if we were here, we would know that we were up there, right? So we already know how far along we've kind of been. So it's interesting, right? So another sort of way to do the same thing is, this is similar. I'll show you. And that we can just say, hey, kind of backing up and going in directions now, is I'm saying, okay, you know what? Why don't you, it'd be nice to be able to sort of focus on a subtree, right? And say, go to this tree and leave your focus there. And so that we know where you've kind of been, left or right. And so we can kind of do that. We can sort of accumulate a list of directions as we go down this tree, which is kind of neat to go, right? So in this go left function, we'll say, the type up here is tree string and a list of directions, and we return the same thing. We'll say, hey, if we've got a node, some value, don't care what that value is, and we've got some direction, L, that's with a bunch of other stuff, then, or sorry, no, that's the tree, I'm sorry. So we've got a node with some value, and at least one subtree, and a list of directions, then return that subtree, and then append the left direction to the list of existing directions. All right, so all this is saying is, as I'm going down this list, I'm going to store where I've been. That's all that means. And this thing just takes care of the rest of the pattern. And this thing over here, you know, Remember, so this thing that needs to have, if you're going right, you just have at least 2 items, and then whatever the third is, doesn't matter whether it's a single or an empty. And so we do the same thing on the right-hand side. We say, okay, if we at least have a second item in that sublist, or set of nodes, list of nodes, we'll go append the right direction, and we'll return that particular tree. So that just sort of looks like, let's see, go left, right. Compose that would say go right. And do that. Well, I'll just show you what the actual portable tree looks like. So let's say we go right, we go left, and then composition is backwards, right? So go right happens first, go left happens second. So, was it good? Yeah. So, I run this. Oh. Right. I'm not doing that correctly. And to give it some initial sort of starting directions, which is the root of the tree, which is nothing. Right, prints out gobbledygook, which is not really direct. You can't see much. But you'll see that you go right, you go left equates to going right, going left down here, right? We have our list of directions that are over there. And if we increase it, so we go left again, you'll see that the only thing available at that point is the C, and there's nothing else after that. So let's say we add another go left. I wonder what happens. I haven't tried this, so let's see how bad it is. It doesn't do anything, right? Because it's that other pattern kicks in. It's like, I got nothing for you. Here's the original node that's back. Right, so let's draw this. The first item is the tree. So that's really nothing there. Let's get rid of one of those lefts, or 2 of them. See what that happens. And it's just sort of focusing in on that particular tree, where that tree was, right? We're not changing anything. We're not replacing it with a bunch of X's. We're just going down a particular tree and noting where we've been. That's all we're doing with this going left and going right business. But that sort of leads us in an interesting direction, because now that we know that we're going left and we know that we're going right, the next step is obviously to keep track of where we've been, right? And so that's sort of where this notion of, sort of brings in this notion of what a crumb is. And I'm going to hopefully ignore. I'm going to use this notion of a crumb. Crumb simply being, we've been here, but we're also going to keep track of where we've been. Okay? So for instance, data, we've played this data type called crumb. And it could be either be a left crumb of a string value, because that's the value that's going to be in our tree, right, at each node. And then the forest of strings, which is just a list of trees, basically. Because remember, on our tree data structure down there, forest is defined as a list of trees. And the tree data type takes a value and then some list of other trees. Just want to make that clear. So the left crumb saying we're just going to store a value and a bunch of trees. Right crumb storing a value and a bunch of trees. Great, now what? Right. So we'll declare these 3 functions called left, right, up. Up is one we have not seen yet, but we'll get to that in a bit, right? So left says, hey, listen, I'm going to take a tuple of a tree and a list of crumbs, because I need to know where I've been or how I'm going there, basically. And so when we get to the first little pattern, we say, hey, if the node has some value and it has at least a left, and whatever the right is doesn't matter, and a list of crumbs, then we're going to return the left tree, left subtree, and I'm going to leave a crumb saying I've been to the left with this value, which is v, and here's the rest of that subtree. And then I tack on that to the list of existing crumbs, if there are any existing crumbs. Right? Pretty straightforward concept there. On the right side, I kind of do the same thing. I'm saying, hey, if there's a node that has some value, and there's a left of that left item in the list, or there's at least 2 items in that list, L and R, coupled with anything else afterward, whether it's empty or one thing, it doesn't matter. I'm going to say, I'm going to return that right subtree, and then I'm going to return saying, I've been to the right, with the current value, and I'm going to tack on the left subtree to the rest of the right subtree. Tacked on to the existing list of crumbs. That's all that does. So let's not cover the up thing. Let's just go see what that looks like. Okay. So let's say left. If we do, what's the type of left? Got the correct thing over there. Let's just do left, right, because fun like that. And so right. I was getting caught out by this. I need to separate the composition from the value that I'm passing to it. So, type of that is correct. I take some stuff in, I return a tree, whatever that looks like, and let's see what does that look like. Holy crap. Right, that's a lot of stuff. Let's just say we've been to the right. What does that look like? That's still a lot, right? Simply because, note that up here, where there's a root label saying L, okay, we're at L, here's the subforest that is all the stuff that's in that tree, subtree. And the last thing is what we need to know, or where did that go? Where's the list of directions? That would be nice if you had like an inspector thing for a data structure.
It's right, right in the middle. See right crumb quote P.
Ah, yeah, there it is. Okay, so from here to the top is pretty much the node. And this array that starts over here, this list, if you will, sorry, list, ends down there. But it says, okay, I've been to P. So let's see what that, remind ourselves what that looks like. Yeah, so it says, hey, I've been to P. And the root label gives a list of nodes that are there. It says, I went down, finding all this is not very nice.
That's your whole poly.
What's
Yep.
that?
That's your whole root.
Yes, it's the whole entire root, right? It
And,
stores
well,
everything.
From your root all the way down your whole tree.
Yes. So let's see what that prints out to be. Let's say I want to go right again to the A, basically. Right, it says AIP, but I'm only drawing the thing, right? If I do what that second thing looks like, it says, hey, here you are.
This kind of starts to illustrate why it's called a zipper.
Yeah.
Because as you're going down, you're pulling things off and sticking them off to the side.
Right.
So it's kind of like you're unzipping the tree as you
Yeah.
go down, because you're
Yeah.
still, everything that you're taking off is now going off in the side crumb structure,
Right.
which is getting longer as you go down.
Yeah. So if you're going down 3 rights, it would be quite a bit there. That looks like there's just that P that's there. So here's an interesting thing, right? So let's say if here's something that's cool. We didn't even talk about that. But now we can kind of go up as well. So we went all the way down, and we went all the way up with a bunch of functions. Right? So I'm going to show you what the up thing looks like. Right? The up function over there, same types, right? Over there. And says, hey, if I encounter, I don't care what kind of tree it is, it doesn't really matter to me. If I encountered a left crumb with some value and a bunch of subforest, forest, if you will, then return a node that has the value that I visited previously, along with the tree that I'm currently at, tacked on to the existing forest that's there, along with the rest of the crumbs that were there. And if I've been to the right, return the right value, the D that's there, along with the forest that's there, the L, I'll tack that on to the tree T, because we have to put that in a list, because it's not a list, it's just a tree by itself. And then return the rest of the V's that are there. So this up thing pretty much just looks at where you've been and recreates sort of where you have been. That's pretty much what it does. Where have you been? I'm going to recreate the structure that was where you were before. That's what the up thing does. So this is all fine and dandy, right? But so far all we've done is traverse a structure, and we can kind of go back up to where we were as well. And so let's see what an interesting thing is. So far I've only done right, up, 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 way at the end, right? So let's say I went right, I went a little further through right, I went up, and then I went left, and then I went up, and then let's say I went left again. Pretty much you can kind of traverse where the heck ever you've been. Go down to the left side of the tree, and maybe go down the right side of the tree. Been way down to the bottom. I'm going to go back up. But, you know what? Now I'm going to go right. Up, so on and so forth. You kind of get the idea that, you know, you're going left side of the tree, then you're going right, then you're going left, then you're going up, then you're going right, then you're going up. It's just whichever direction you feel like going, you can. And without sort of incurring the loss of, I need to travel all the way to the top of the tree, all the way to the bottom every single time. But now, since I'm keeping a history of where I've been and what the route is, I can always figure out how to go back up. And consequently, because I can go back up, now I can go left, or I can go right, and I can go wherever I want in the tree. And traversal becomes easy, right? So traversal is great, right? This entire notion of having a left and right and storing where you've been, that's pretty much all a zipper is. Zipper is just a list of directions with where you've been and your data structure, whatever that might be. And so modifying is pretty easy. Modifying, if we take a function, f that converts a string to a string, whatever that string might be, and applying it to the existing zipper, it's pretty simple. It's just saying, hey, I'm going to return for any node that has a value, has a bunch of subforce, or has a force, or not, it doesn't really matter what that is, and given it a list of directions, pretty much all I'm going to do is return a node and map that, apply that function to that value, and return the rest as is. Note over here in this modified structure that we're not changing anything, or rather, we're only changing the value, right? There's no list of directions. There's nothing in there. It's just saying I'm going to do whatever it is at some point. Right? The modify has nothing to do with traversing. It's two separate things. So let's start fresh. Let's draw a poly. Let's say we want to pick a random letter to what we think is harder, because they're all pretty easy.
S.
S, okay, that'll work. So that guy is left, right, left, left, right, left, left, right. So, left, right, left.
Future.
Good. So we've got that little type checks, hooray. So now what we want to do is we want to modify. And let's just say we'll replace it with, because I'm very original. Right, is that type check? No, it doesn't. And it does not type check because I know that. Show that again. I'm going to have to introduce the basically $sign there and the $sign there. For those of you all not familiar with $sign in Haskell, pretty much says I'm going to value the rightmost first and then move to left. That's all it does. So basically, that gets evaluated, that gets evaluated, and then that gets, this entire thing that gets evaluated gets passed as a parameter, second parameter to modify. That's all it is. So now that we have that, hooray, we have a zipper, but now we can print the bloody thing out, so let's do that. Right, hooray, we modified a value down there in the tree somewhere, but now we need to get access to it somewhere. Let's go see what that looks like, right? Let's store this. Let's just say zip tree. So now let's go up, and up, because we went left, right, left. That's 3 downs. We'll just go 3 ups. So say zip tree. Draw the first element tuple, and then voila.
Nice.
It's down there. Right. So our new tree was pretty much that. Or, yeah, it's pretty much that, but it has references to the rest of the tree elsewhere. And by doing up, 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 we go up, 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 and we draw that tree. So that's pretty neat. Hooray, we modified something. But there's some cool stuff too. But since you're already down there, you're modifying, attaching is not that big a deal. Right? If you want to attach a subtree to an existing tree, that's also kind of cool. To be able to do that as you're traversing this data structure. In this case, this attach is not a generic attach. It pretty much attaches to the left of the tree, because I'm lazy. Because doing it arbitrary location in a subforest is more lines of code and I didn't have time. So attach is pretty much saying, hey, I'll take a tree, I'll take a zipper, which is just a data structure and a list of directions, breadcrumbs of where I've been. And as long as you give me that, I'm going to return you a new node with the existing value, but I'm going to append that tree they gave me to the left of the existing forest. And return you the same list of directions that were there previously. So what that kind of looks like is, let's say, all right, I'm going to do something. Say I put attach this node of Baz. Baz is cool. That. Where am I? Alright. Pretty much went up once, up another time. It attached the node Baz to the left side of the forest. Right? The yellow line. Prepended it basically. And so now we're over here. So now we can go up once more. Right, we're at the top. Paul Basley won Fubarchip. Whatever that is. But you can kind of see how if you mix traversals with modifications and do some cool things, you can separate the two even better. Because you can test your modifications separately, you can test your traversals separately, and you can just compose them together when you need to. I've seen an example online where they implemented a zipper data structure in Java, and that was about 6-7 years ago, and it probably still works. It's not saying that you can't use a zipper, or zipper's only meant for functional data structures or functional language, because you have the same problem in any language. If you have any kind of tree-based structure or any data structure and you want to efficiently traverse and modify things at the same time, you're going to have the same exact problem. And especially if you're doing lots of editing or lots of changing, you'll have to use a zipper. Apparently Clojure makes a whole bunch of use of zippers. I don't know enough about Clojure to know what it does with them. But a lot of text editors end up using the zipper data structure simply because you're typing text, especially in an IDE, you're modifying things anywhere willy-nilly. And if it needs to traverse your list of characters, sequences, whatever it is, and do some analysis behind the scenes for that local part, focusing with those directions is really helpful for that.
Yeah, like undo trees.
Yeah.
Like that.
If you're creating like a new AST underneath a function or something like that. So it doesn't have to go read all your code again and then build the entire AST again all over the place. Like Microsoft's new Roslyn compiler in C#, what they're doing, and I think it's pretty much in C# so far. The guy, Anders something, who writes the C# compiler.
Ellsberg.
Yeah, Ellsberg. Yeah, he was saying that their new compiler services sort of do that. If you're in the IDE and you're typing in the middle somewhere, it pretty much starts there and then builds everything around it. It doesn't do top-down everything anymore because it's way quicker to look locally, provide you inference as quick as possible, and then build the rest of the world out. So pretty sure this is somewhat used in that space as well because I can see how it would relate. That's all I have for the zipper structure. Any questions? It's not particularly complicated. It's just when I sat down and worked it out, I was like, get it.
So what's the memory complexity? Because I would be worried about reallocating nodes all over the place. Like, it seems like you're going to end up with lots of memory duplication.
Yeah, so if you don't have, in an imperative language, if you're trying to do immutable structures in an imperative thing that doesn't have structured sharing, you're going to blow your memory out. That's just a given thing. Simply because if your data structures aren't sharing the same values, it's a problem, right? But since you're sort of storing references here, pointers, if you will, in Haskell, and Haskell has shared values for pretty much everything, not a problem. As long as your data structures, like in Clojure, they use the same thing. They use persistent sort of shared data structures. And there it's not a problem as well. Yeah, your data structure kind of needs to support that. Because if you don't, if you're copying everything every single time you're traversing the thing, it's going to be expensive, for sure.
All of those should be O1
Yeah.
complexity, and then if you've got a function that moves you up all the way to the top, it's On to the height of the tree.
Yeah, I'm not so worried about the time complexity. That seems really low. I am worried about all the memory allocation that you're going to have to do. So,
Well, each traversal is going to just add a couple of links. But it's like you're saying, it's sharing all the tree. That data is not being duplicated.
Yeah.
well, that's something I'm going to do. Okay.
Yeah.
Yeah, your path, well, yeah, how many items are in your crumbs is
You
really
also
the only
still
thing that's
point
growing.
to different parts of your tree.
That's the
with
only thing
pointers.
that's growing. You're not recreating the nodes or
Right.
sections of the tree.
Yeah.
It's actually very efficient.
Yeah, you're not copying anything. There's no copying going on. It's just referencing. So pointers are cheaper than full copies.
Oh, yeah.
So are you saying that the zipper data structure is the only thing that grows and shrinks as you traverse?
Yeah, the data structure is the only thing that grows,
Okay,
pretty much.
pretty good.
It'll shrink with garbage collection, but it will only grow. That's kind of the neat part about it.
And
Yeah.
actually, as you go up, then it shrinks back. So it's not a constant growth, right?
No, well, then GC has to kick in and
Yeah.
take away
Oh.
all those things that you've been at previously. Because if you're not using it, then GC will come along and say, okay, bye-bye.
So what would be an actual example of using this for like real life code? Like, so you mentioned text
Text
editors doing this.
We're just traversing, if you're constantly having to traverse a bunch of data structures and edit them as you're in them, this is where you would use it. Or if you're just ad hoc willy-nilly doing it, this doesn't make too much sense.
So Xmonad used this a long time ago for its preserving the window structure in a window manager. So windows
Okay.
would be items in this tree, and as you were moving your kind of focus around, the zipper would shift everything around to meet that, and then you could have areas that have nested applications you could go down
And you
to.
could undo those focuses.
So it wasn't really for performance or anything. It was just a convenient abstraction to represent a context and how I got there and how I can start going back out the way I came.
Yeah.
Yeah. The traversals, basically, is where it's really important. someone ended up making a file system based on the zipper, and that's kind of cool too, because you can go as far as you want, but then you're like, hey, I need to go here, go back where I came from with that list of directions that I had previously. And then they kind of added some other properties onto it as well, where you can remove things, destroy things, but they're all sort of done atomically. I don't know how, but that was cool. Just reading about that.
Which is kind of what Clojure does. And,
Yeah, so I don't know if they were, the Roslyn team was using tree stuff either, but the intersection of memory and mentioning the Roslyn team, I do know that they had the early revisions of the immutable collection stuff that they were adding. The Roslyn team was blowing up because they were treating it kind of like they treat strings and just, you're always giving them copies of everything.
Copies of everything.
Right?
Yeah.
And they quickly ran into that, and that, the language team actually had to go back, and Anders and them did the differencing, you know, immutable differences, and now they're, I don't know what other structures they brought in to, you know, these 9 lists, immutable lists are your list now, right, or whatever, you know, depending on your, whether, just whatever enumerables and things that they were doing there, so anyways, it's an interesting, there's a couple interesting articles, blog entries that a couple of that team wrote that interesting to follow, like, tingling your brain around those things.
Yeah. So that was sort of about all I had for the zipper stuff. Did you want to do your?
Sure. We have HDMI up there.
Yeah.